Let's talk about another short-term type of plasticity, which is synaptic depression. Which would reduce the strength of a synaptic signal. We mentioned before, right, that we think it's due to a decline in neurotransmitter release. Oops. Decline in neurotransmitter release. And in order to show this, we can look at some experimental evidence. If we look to the panel to the right here, panel C, every little dot here is a stimulation that's given, and you can see the change, right? The postsynaptic response, and that's in millivolts per millisecond. Okay, so if it changes, if we give a zap to the cell presynaptically, right, and we get some dot here, which suggests that we get a change of 80 or 90 millivolts per millisecond, right? So we think that the axis is weird here, but we think that the postsynaptic cell would be depolarizing, right? And it's changing by some ratio. It's depolarizing at a rate of 90 millivolts per millisecond. So a strange way to look at it, but that's the idea. So if we stimulate here at the very beginning, right, we see a change of 100 millivolts per millisecond, and if we stimulate maybe here, we see a change of maybe 90 millivolts per millisecond, and if we stimulate here, right, and you can see the time, right, so if I stimulate here, if after 5 milliseconds, we see this decrease in millivolts per millisecond here, right? And so we think that we might be using up some of our pool of synaptic vesicles. And then in this darker shaded area, we stimulate with a tetanus. Okay, and so let me put what a tetanus is up here. Tetanus. It's a rapid train of stimulations. Okay, so tetanus, to tetanize the presynaptic cell would be like, brrr, right? Stimulate, 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 more than you can just measure, right? It's a rapid succession. And what that does is create this really, really clear, this strong and fast synaptic depression where we get rid of essentially all vesicles that are available. So we drop way down here, right? And so during this tetanus, right, we're basically changing the postsynaptic membrane potential like not at all, right? No millivolts are changing in any millisecond. Now, when we stop the tetanus, we do rebound, but we rebound in such a way that we're always lower than the slope that we started with here, right? So the evidence here is that as we stimulate, right, we see the postsynaptic response gets lower, it decreases. And especially during a tetanus, right, this postsynaptic response is basically zero. Now let's look and see what happens when we take some calcium out of the solution, right? So the conditions here were under normal calcium. And as you know, calcium is required in order to release neurotransmitter. So let's reduce the amount of calcium. So another line of evidence, right, is we can continue this experiment. And now let's see what happens when we reduce the calcium. So if we reduce calcium, the thought goes that we would reduce the number of quanta, which means we'd sort of keep the pool of vesicles and continue to release them over time. And so let's see what happens here, right? Well, at every point, they stimulate, let me draw this or explain this better. Every point that they stimulate the presynaptic cell, they get a postsynaptic response. And note that this response is pretty linear. And even when they tetanize the cell, right, they don't see this depression anymore, right? So there's basically not nearly the depression, although it is seen a little bit here as the slope is negative. And it goes back, right? The release and the response goes back to the basal levels when the tetanus is over. And when they add calcium, right? So in this panel, they're adding calcium. Stimulate, a dot as a response. Stimulate, a dot as a response. Stimulate, a dot as a response. There's no change in response. When they tetanize, you can see this slope is pretty much the same, right? So there's no real change. There's no real depression in the tetanus. And that, this decrease here is because we're not tetanizing anymore. And now we go back to this type of response. So at reduced levels of calcium, right, we reduce the amount of synaptic depression, and the evidence for this is that we can still see we still observe similar responses. Okay, under these conditions, under these low calcium conditions. And so normal calcium all the way down to, what is this, 1/10 normal calcium. So does this make sense? When we reduce the intracellular calcium, we reduce the amount of synaptic depression and still observe similar responses, right? All the way through here, right? We observe similar responses. We don't see any depressive responses at all. Because the pool of vesicles isn't depleted as quickly. And so our conclusion would be, right, high rate of neurotransmitter release could lead to more synaptic depression, right, because we exhaust our reserve pool. You can see that in this figure part D here, right? So this is the relative amount of transmitter release and the relative amount of depression. And so the more transmitter release you have, right, pretty much the more likely you are to have depression, and the greater the degree of depression, okay, synaptic depression. So if we've got, 5 times the amount of transmitter release that we had initially, we would expect to see substantial depression, okay, because we get rid of, right, we use up our pool of neurotransmitter. Now you may have noticed something funny when we look at this intermediate level of calcium, right? We're going to try to look at long-term, or not long-term, excuse me, but synaptic depression here. And so we've reduced the amount of calcium, and we stimulate and stimulate and stimulate, and then we stimulate tetanus, right? And we see this increase in activity here, right? That's certainly the opposite of synaptic depression. Now we see synaptic depression after, right, during this tetanus, right? Here's the synaptic depression and this downward slope. But what's up with this increased activity? And it seems counterintuitive to everything we just said, right? Well, this is another type of short-term plasticity, short-term potentiation. And grouped in to short-term potentiation, and we'll talk about it at the same time, is augmentation. Potentiation and augmentation. All right. Really, I think the only difference that we'll talk about, the primary difference, is the duration, right? So potentiation, this is going to be really seconds to minutes. Whereas augmentation is maybe just a couple of seconds. 1 or 2 seconds, right? So the time frame is different. This is really, seconds, tens of seconds, 20 seconds, 50 seconds, 3 seconds, 4 seconds, 5 seconds. That's going to be our time scale difference, okay? And we can see what this looks like, at least with respect to potentiation, in part E, right, in figure E. Stimulate, response, right? So they're measuring this in millivolts postsynaptically. So they're going to stimulate a presynaptic cell, right? The experimenter stimulate a presynaptic cell. And they get similar responses, right, around, what is this? I can read my own axis here, I scribbled over it. Right around 3 millivolts. So when they stimulate in the postsynaptic cell, they see a change in 3 millivolts. But then they give this tetanus, like we talked about, right, this rapid train. And then when they stimulate after the tetanus, their response almost doubles, right? And so again, you can see our time window here. You're talking tens of seconds. So this definitely looks like potentiation. And so what this is called, this is a type of potentiation called post-tetanic potentiation. PTP, post-tetanic potentiation. And it's interesting because the PTP, the post-tetanic potentiation, can last longer than the tetanus itself, okay? And again, the mechanism here that we think is calcium. We think that this is calcium entry, right? So, I don't know, maybe these are interesting points here, that the effect, this PTP, can be longer than the stimulus, right? Than that particular tetanus. And that, again, we think that this is calcium dependent, and that increasing calcium via tetanus causes so much calcium to come in to the terminal, the axon terminal, right, that it really never goes down, and that any stimulus following the tetanus leads to this large, or twice as large of a response in the postsynaptic cell. So calcium dependent still. And so that's what we think is happening in this middle figure in C. We see both effects occurring, right? When we give a tetanus here, we see increases, right, potentiation, because of the large increase in interest in the cell calcium in the terminal, but then we're exhausting how many vesicles are present, and so we see synaptic depression. So this is a combination of both mechanisms. It's both potentiation and, right, a post-tetanic effect, and this depression, the synaptic depression. I'm not going to differentiate augmentation too much, except that augmentation would go away sooner, okay? And so that after the train of stimuli here, right, this is still, right, so after the train of stimuli here, if we stimulate even 100 seconds after the train, we still see a fairly substantial increase, right? We're still getting, compared to 3 millivolts, 4.5 millivolts change in the postsynaptic receptor. So this is thought to be, and I don't want to use the term long-term because it's not quite that long-term, but it certainly lasts longer than augmentation, which would just be a few seconds, okay?